Hello everyone, my name is Rahul and welcome back to my channel DevOps Forge. Today we are going to start a playlist on Git where we'll be learning each and every concepts of Git in detail, and we will also see that why Git is much more efficient and fast than other VCS tools in the market, right? And you will never be able to find any explanation video like this before, because we are going to deep dive into the Git internal architecture, their concepts, and you will never be afraid to use Git from now onwards, because you will get a clarity that how Git works. And it is actually very important because Git is widely used by the IT companies, and it is used for their version controlling, storing their repository, sharing the code, right? So you need to learn each and every concepts in detail so that you can utilize those knowledge and use Git, right? So without wasting any time, let's just get started. Suppose you are working on a document, right? And let's say you have created a document and it says presentation, right? Now you think that, okay, today I'm done with my work, I need to save this file, and you save it as final.docx. Now the next day you come and you think that there are few changes which I want to make to this particular document, so I will make those changes, and then you add this and save this as final version 2.docx. Then again you make some changes and you created a new file, you say final. Then again you make the changes and you store it as this file name, and then the actual one, the final file you have created where you have added the changes. But after few days you come back and you want to take a look at this document, right? Because you want to share it to your colleague so that they can work onto it. But now you are confused right now that which one is the file which has the latest changes and which one is I need to share with my colleague. So in this way you get confused and you may miss some of the important changes which you have made, because you don't want to choose that file which is outdated, right? You want your latest changes whichever you have made, and you want to share it with your colleague for maybe a presentation or for maybe sharing your code, anything it can be, right? So this is an actual nightmare for the developers or any person who is working on IT field, which is why the Git was introduced, and version control like Git or any other tools were actually introduced in the market so that they can solve this particular problem. Now you clearly understood why we need version control. Now let's see what version control actually means. So let's start with a simple situation. Imagine three friends are there, A, B and C, and they are working on a particular assignment, right? So one person, A, is working on introduction, B is working on the body, and C is working on the conclusion, right? Everything looks fine in the beginning, but then they start sending the document to each other over email, and one person edits the file and sends it back. So let's say B has made some edit and sends it back to A, and then C has also made some edits and sends it back to B. So there are two versions of this particular file right now, correct? And nobody knows which one to keep it, because if you choose one version, the other person's work will disappear. This is exactly the kind of problem version control solves. Now imagine this situation not with 3 people but with 30 developers, and not a single file, instead thousands of files are there, right? And without a proper system, managing changes becomes almost impossible in this scenario, correct? So version control is simply a way to track changes in files over time. That's right, it tells you who changed something, when they changed it, and what exactly changed. And most importantly, it lets multiple people work together without overwriting each other's work. But version control didn't always look what we use today, right? We use Git today, but it didn't look like before. In the beginning, so let's see the stages how actually version control evolved. So in the beginning, version control worked only on your computer, right? So you could save different versions of files, right? Just like we saw in this example, where let's say you were working on that presentation and you could save multiple versions of that presentation locally in your own computer or in your own system. But that actually helped the individual, right? It didn't help the teams to collaborate and share files, so they had to share file manually. That's right. So the next step was centralized version control. So let's say centralized version control. Okay, here all files were stored on a central server. So this is your server, right? And all files, okay, there are multiple files, so they were particularly stored on a server, the central server, and everyone used to download the file from that particular server, made changes, and then sent it back to the server or upload it back to the server. So this actually solved the collaboration problem, because now teams were able to collaborate. But there's one problem to it as well. What will happen if this particular server will crash, right? Your all files will lost, and the people who were working on those particular files or that particular code will not be able to collaborate or share, or they cannot upload it back to the central server, right? So everything dependent on only one machine, which is why this was also discarded, and now the latest system is distributed version control system, where Git comes in the picture, right? With Git, every developer has a complete copy of the project history on their own machine. So in your own machine, okay, this is personal machine, you have the copy of the entire project inside your own system, right? Not just the latest files, the entire timeline of changes, whatever is happening inside a particular project, correct? And it also means developers can work without internet and sync later. So let's say you don't have internet and you are working on your local machine, right? So you can share whatever changes you have made to a particular file back when the internet comes back, and you can commit those changes to the repository, and then it can be shared to your other team members, right? So this also solves the problem of where you need to upload the files every time you make any changes to the central server, right? And you have to be connected to the internet to do that. But working on your own local machine by creating a branch will not hamper the progress of other developers' work. So in this way, whenever the internet comes back, you can sync your project later, right? So now if the interviewer asks you, is Git a distributed system or centralized system? Now you know what to answer. So you must say that Git is a distributed version control system, right? It means that it allows developers to work on their own local copies of project, right? While still enabling them to push changes to a shared repository, right? Because a particular repository is being circulated or shared across all of your team members, right? And they are collaborating and working and then sharing their changes to the shared repository. Now let's see what are the capabilities of Git. Okay, so first is version tracking. Now Git follows all adjustments done in one record and letting you revert to old releases without having any trouble, right? Which is what we call version tracking. Second is, of course, collaboration. So different programmers can work on a similar task at the same time without clashing. That's right. Third is the branching capability of Git. So you have the option to create multiple branches, distinct branches for new attributes or bug repairs or writing any of the test cases. So this is the example where you need to create the branches. Fourth is distributed system. Now every programmer has an entire version of the project. So this is a project and every programmer or developer has the entire version of that project, right? And implying that this is a decentralized software where every programmer has the version of it and they are making some changes. Now they have v1, v2, v3, but it doesn't matter because they are working on their own branch using the branching capability, and they will commit those changes back to the shared repository, and they can merge it whenever they want according to their need, right? Fifth is log of commits. So with this feature, Git maintains an account of all commit actions. So log of commits means it actually maintains the record of all commit actions, whatever the commit has been taken. So let's say multiple developers are working on it. They are making n number of commits. So all of the commit history or the records will be present in that particular shared repositories record. Yes. And anytime you can revert back to the changes, or you can track whatever the difference is, and you can just get back to your working code if anything goes wrong, right? So another big reason Git became popular is branching capability. So in older systems, creating a branch was heavy and slow. So developers avoided using branches unless absolutely necessary. But in Git, a branch is lightweight, right? You can create branch in seconds, and because of that, developers started creating separate branches for features, bug fixes, experiments, or POC or anything, right? Instead of everyone working in the same place, each person works in their own space and later merges their changes back, right? In their local machine, everyone is working on their own confined space, right? And they are working on their branches, on their particular branches. So no one is actually clashing with another people's work because they have their own branches with them. Even though if they commit back to the shared repository, their own version will be there. So if let's say this person A and this is person B, so he actually created a branch and then he committed those changes to the shared repository. Now the v1 of person A will be stored in the shared repository but as v1 only, and the v2 of second person, the person B, will be added to the shared repository but as v2, and they can merge their changes and create a new version called v3, right? Because their changes are into different branches, that is why their work is not clashing anymore, correct? So by this you have clearly understood what are the capabilities of Git, right? Why we need version control, what is version control, and over the time how version control actually evolved. The next very important concept in Git is Git Internal Architecture. So we have Git Internal, just a minute. Well, rather I just like to type it, okay, and I will say Git Internal Architecture, correct? Now let's see what actually Git stores inside their internal architecture. So now we are going to go one level deeper, not commands, not the workflows, we are going inside Git itself. Because once you understand what Git stores internally, Git stops feeling confusing and it starts feeling logical. Most tutorials never explain this part properly. I've seen many of them while I was preparing for my interviews. I've seen many of them, but nobody has even shared a bit of this information onto their channel or anywhere, right? So which is why I get to get confused a lot of times, and I used to get scared of Git, because it is very important to understand Git. Each and every IT company is using Git, and any of your wrong action could entirely crash your project or your repository, right? Which is why this is very crucial to understand how does Git actually work, right? By this video or by the end of this playlist, you will never be scared of committing or creating branches or doing resets, checkout, or even merge conflicts. They will start making much more sense. So let's begin from the core idea, right? And I used to think that Git actually store a file in any of their server, and then they show it to ourselves, like the developers, and the developers pull those files from the server. But that's incorrect. So Git does not store files the way most people think it does. Git actually stores objects, right? Now you will think, what are objects? We will get back to this, and you just understand it in this way, that Git, everything in Git is an object, right? And there are only three main ones you really need to understand. First is blob, second is tree, and third is commit. So let's start with the first one, which is the blob. Okay, so Git stores content, not names. Now what does that mean? So actually Git stores file content as blob. So you can say that Git stores the file content as blob, right? And let's see how it does it. So first of all, let's see that you have created a file called notes.txt, and it has hello world written into it. Okay, now what you have done is you have added this into your Git system, and you say that git add notes.txt. Now what will happen is the content inside that particular file, which is what? Your hello world, right? It will be stored as a blob, and only the content, nothing else will be stored, right? Your file name or anything will not be stored, only the blob will be stored. So this hello world is going to be stored inside the Git architecture, right, as an object, and it will also have the blob ID. Let's say A1, B2, C3 and D4 is the blob ID. So Git over here in blob, Git didn't store the file name. Okay, let me add this. It didn't store the file name, no folder name, and no metadata, right? What it stored? It stored only the content, just content. Now let's say you have two files, right? Let's say todo.txt is one file and readme.txt is another one. It both have hello world as their content, right? Now what you did, you again use the git add to add this right over here as well, and the content is now stored as a blob, which is hello world. Similarly, the content over here is also stored as hello world, right? Now this will be stored inside a blob, correct? And blob is an object which is going to be stored inside your .git folder, and .git have a folder called objects where this where actually you have your object database, right? And you have the blob over here, and content only is present inside this blob, right, along with the blob ID. So Git reuses the same blob because the content of both of these text files is same, which is why Git doesn't store it twice. It actually sees that, okay, todo.txt is also having hello world and readme.txt is also having hello world. So let's save it as a single blob, right? Single blob content, correct? And in this way, if you have same content, then you will have same blob ID and no duplication. Understood? So Git stores file content as blobs, and blobs have no name, no path, no metadata, just raw content, which is in this case hello world. And identical content is stored once and then reused. Right? So you understood what actually blob is. Now we will move ahead with our next object, which is tree. And from here you will going to get a gist of it, that why this blob object is being created and how is tree referencing the blob. So so next object is tree object. So let's say you have a project, right? This is your project, and inside this, let me just remove this one. And inside this project, what do you have? You have app.py, you have config.json, and then again one folder which is called docs, and inside this you have your readme. Correct? Now blobs alone are not enough in Git to be stored, right? Because you need file name, because in this case, if let's say there are multiple files with the same content, then in that case the Git will get confused, right? So blobs alone are not enough. So blobs don't store the file names and they don't store the folder relationship. So over here you see that inside project we have docs have readme file, and app.py, config.json. So these are actually having a relationship between each other, right? And which is what blob is not storing it, correct? So what actually tree does is, tree object stores the file names. So whatever the file you see over here, app.py, config.json, all of these files will be stored by the tree object. Then they store the folder names as well. And very important thing what they do is they reference to blobs. And later we will understand that how does they reference, right? So the tree simply says that this file name points to this blob, right? Let's say there's a blob inside a file, blob content, right? Inside a file, right? And the file name is, let's say, todo.txt. So it's tree's job to map this, that todo.txt has this particular blob content, which is hello world, right? Now let's clearly understand trees by an example. Okay, so first of all, the first point is blobs store content only, store content, just data, right? Now let's say this is your app.py and it has the content print hello world. Okay, and now what blob will do is blob will save this content and it will create a blob ID, let's say A1 B2 C3, right? Then you have config.json as well. In our particular example we took over here, you see in our example project we have app.py, config.json, and then this particular folder which will have readme.txt, right? You have added some of the configuration, and this is again stored into a blob, and now you have D4, E5, F6 as the blob ID. The next thing is you have a readme.txt inside docs folder. correct? Or let's say readme.md. Okay, and it has some of the content, whatever content you like to add over here. And again, this is stored as a blob, 7G, 8H or 9I. So this is the ID of the blob. Now this is what blob is doing, right? It is storing only the content. Now what about tree? So in parallel, let's just draw tree as well. Okay, what it is doing? So tree stores the structure, the map. So let's create a table and understand this, that you have a name, let's say the type, and then you have points, or you can say pointer, right? Then your first file name is app.py, right? The file name is app.py. Then you have config.json. Then you have docs, correct? And let's create a separation over here and let's add it, right? Now the app.py is a blob stored over here. Then again it is a blob, but docs is not a blob. Instead it is a tree, right? The pointer is, you have A1, B2, C3, then you have D4, E5, F6, right? And let's say this doc is a tree which has T1, A2 and B3, because files are stored as blob, not the folders, right? We have understood over here in the blob section that blob does not store the folder, right? It does not store the folder. Now again, if you want to store a file content, then it will be stored in the form of blob. But what will happen if it is a folder again? So inside our project we have a folder, right? Over here, a folder inside a folder. So if this particular, and if this entire project is acting as a tree, T0, let's say this is T0 and this is a tree object. So inside this you have docs folder, which is why we are saying this is tree, right? And it is a T1. Okay, so I'm supposing this as a T1. Now what will happen? Again, it will be break down into this particular table where we have name, the type and the pointer. Now the process is same. You have readme.txt or md, right? And the type is blob, and then you have the blob ID. Now you understood how tree is actually referencing the blob and how the mapping is done, right? So this is the way how it actually maps, right? So this tree is actually representing the docs folder, and this tree is representing the project folder, the example project which we took. Correct? So in short, let's just revise one thing is, if blob is storing a content, right, then tree is storing a structure, right? Tree is storing a structure, correct? And trees don't store the file content, they store the names of the file plus the folder structure, correct? And it references to the blobs. In this way, you see, first what Git did, Git's first of all, it just resolved this particular project as a tree, right? Because it has folders and it has files, which is what the job of tree is, to resolve this into a particular tree. Then inside that tree, because this project is a folder, so this will act as a tree, and inside these we have files. So these files have content, which is what Git resolved, that these are going to be blobs. So they the Git actually stored the content of those particular files into blob, and it added the blob ID. Now the pointer is this particular file name, which is app.py config.json, is being mapped to that particular blob which has the blob content, right? And if we have a folder, a subfolder inside a folder, then it will again be treated as a tree, which we can call a T1 in our case, and then again it will be get resolved to a blob, and then the mapping will happen, right? This particular file name will be mapped to this particular blob, right? In this way trees actually work. So you clearly understood that how trees work, and you can say that tree is behaving like a map, where in map you store key value. Just a minute. You store key value, right? Key and value pair. Similarly, in tree we have file or folder as a tree, and the value file and folder as the key, and the value is the blobs or the blob content, right? So you clearly understood what is blob and what is tree. So the third object is commit object, and this is very important one. Commit object. So most people think that a commit is a snapshot of files. That's actually partly true, but internally a commit is a pointer. So commit is actually a pointer, right? So what does a commit contains? It contains reference to a tree. So similarly, the tree has the reference to the blob. In similar way, commit has the reference to a tree. It has the reference to previous commit as well, because whenever you are working in Git, you have multiple commits, right? So C1, C2, C3, and all of these references are being stored into the Git using the commit object only, right? It also has the author name. So it stores the author name as well. It stores the timestamp and whatever the commit message you add, right? So whenever you do git commit and -m, then you store some message inside the inverted commas. So this message is also stored, right? So a commit is basically saying that here is the project structure at this moment in time, right? It just shows the timeline as well, and it does not store files directly. It is a pointer, so it points to a tree, and the tree points to a blob. So the flow is commit is pointing to a tree, and in return tree is pointing to a blob. Now let's understand this with an example. So let's say you have a commit called C0, right? Inside this it has the tree which it is pointing to. Let's say it is T0, right? The parent we don't know yet because we are starting as of now, so it's null. And the author is Rahul, and the timestamp, whatever the timestamp is, and let's say the commit message as well, right? Whatever the commit message I have added. Now I made a different commit, right? So initially I branched off from the main, and then I made the first commit. So in this case we don't have any parent to the previous commit, right? But now the parent of C1 would be C0, correct? Because it creates a linear history as of now. And then the same information we have, but now we have a different tree, right? It is referencing to, or it is pointing to. The parent is C0 and the author is Rahul again. Then we have timestamp, then we have commit message. And similarly, if you have created a different commit, another commit, let's say C2, you will have all of this information, but now the parent of C2 would be C1, right? So commit object in this case is referencing to a tree, right, which we can call T1, and it is referencing to a tree. Okay, so let's just create one. So this is the tree T1, and whatever the parent is C0. I'm just visualizing these two, right? Sorry, this particular one, uh, and to reference it from the tree and then the blob, so that you can see what actually happens. Then, or let's do one thing. Rather than getting confused over here, I will do what I will do is I will just similarly extend this particular diagram. Okay. Now I have said that commit is pointing to or referencing to a tree, right? So let's make a tree object over here. Tree object. What will it have? It will have name, it will have type, and it will have the pointer, right? And inside this you have app.py, you have config.json, and you have another tree which is called docs, right? And these all are blob and blob. So you have pointers over here, the blob id, and then each one, let's say b1, b2, and this is a tree, so we'll call it t2, right? So again it will create a tree object like we have seen in the previous example, right? You have two objects, right? So I'm just visualizing this part over here. Yeah, so again the docs will be considered as a new tree object which will be called t2, and the name, the type, the pointer, and now we have readme.md, the blob is the type, and then we have a blob id called b4. Then again this tree will be pointing to a blob with the blob id, all right, blob content, and it will also have similarly the blob content and the blob id. Same way over here as well, not for this one but for the b2, blob content, blob id. Now you have understood the whole picture, right? That what commit is doing is commit is referencing to previous commits as well, right? C0, C1, in this case for C2, C1 is the parent, for C1, C0 is the parent. It is referencing to the previous commit as well. Then a particular commit is referencing to a tree. In return, this tree is referencing to a blob as a map, and right, and if you have a subfolder structure inside a project, then it will be considered as a tree again, which will then again reference to blob. So this is the entire architecture, what is happening internally inside Git, right? So the chain is commit, which is referencing to two things, First is commit history as well, and then tree as well, and tree is referencing to blob. Now let's understand how does actually Git is tracking all of these objects, or where does it storing all of this information. So the next topic is SHA or SHA hashing, right? So this is actually how Git identifies everything. So Git uses something called SHA hashing, and every object in Git gets a unique ID. So whatever object you have seen so far, right? So whatever objects you have seen so far, it gets a unique ID, right? And this ID is created from the content itself. So if a file changed even slightly, the hash also changes completely. So let's say you have two file 1, file 2, and over here you have hello world, and in the file 2 you have hello world but with an exclamation mark. So these two files have a different IDs. So let's erase this one. Different IDs, right? And it is being stored into Git differently, right? So Git uses this property to detect changes instantly. So whenever you are just developing a code, right, you have added some code, and next time if you have changed anything, then what will happen? Git will identify the content, right, because it is using SHA hashing to provide a unique ID to this particular object, which is blob content in this case, right? So if anything changes in this, then Git is actually using SHA hashing, right, so that the ID will be changed in the next iteration, and then Git will be able to track that. Okay, so this particular file has been changed, and now this particular file has to be committed in the staging area and then pushed to the repository, right? So let's understand the next concept, which is why Git is actually very fast as compared to other version control systems. So many version control systems store differences between files, right? And Git does something very smarter. So first point is we are understanding why Git is fast. Okay, so Git stores content as objects. You have seen this one, right? And it references them using unique IDs or hashes, right? Using the SHA hashing. So if a file hasn't changed, Git doesn't store it again, right? So let's say you have a file, two files, right? File A, file B, and you have cloned this repository into your local system, and you are not working on file A, instead you are working on file B. Since the file A content has not been changed, so the hash ID of this particular file will not change, and Git will not store it again when you push any new changes, because you are working on B, right? File B. You are not working on file A. So the hash will not be changed and it will not store it again, right? Which is why the Git is fast. And it simply reuses the existing object, right? We have seen this example. It is reusing the existing object. Also, most operations in Git happens locally. Git operations take place locally, right? Which is why you are able to make changes in seconds. You are able to branch off in seconds, right? Next point is commits, branches, or branch creation, or switching the branch. Switching branch is done instantly, correct? Because it is into your local system. So because Git is mostly moving the pointers, not it is copying the files, right? We have seen how Git is Git points or uses the pointers to reference their objects. So Git points to the references and it actually reference the objects. It does not store the entire file, or maybe do not copy the entire files again and again, right? One misunderstanding which is common in Git is snapshot versus diff storage, right? A lot of people think that Git stores differences between versions. So v1, v2, v3, and a lot of people think that Git is storing the differences between them, right? That's not exactly true. Git stores the snapshots. Every commit represents the full project state at that particular time. And here's the clever part. Git doesn't duplicate unchanged files. Like I've said in this example, if the file content has not changed because of SHA hashing, it will have a particular hash, right? It will not be changed if you have not changed this particular file. So in this scenario, Git acts very cleverly, where Git doesn't duplicate the unchanged files, and every commit, so C0 or C1 or C2, every commit will have the current state of the entire project, right? Whatever project you have, it will have the current state of the entire project each and every time you are making a commit, right? And this is why restoring old commits is very fast and efficient. So Git already knows that exactly where everything is, right? And it doesn't need to rebuild everything each and every time. Now let's understand one more concept, which is the commit graph concept. Okay, so how actually commit happens, right? What happens when you commit any changes? So all of this needs to be understood as well. Commit graph concept, right? So Git stores history as a graph, you know it, and each commit points to its parent. In this example, we have seen that each commit is pointing to its parent, right? So that Git can reference to the previous commit, correct? So let's take one example where you are creating a simple chain, right? And it is a one timeline, where you have A, then B, then C, and then D. So this forms a linear chain, right? Now what will happen when a branch appears? So this, let's replicate it. A, B, C, and D. Now you have branched off, right? So you have a new branch with your E and F as the changes. So now Git has two timelines. First is this one and second is this one, right? And one main branch you have is A, B, C, D. Let's say this is a main branch. Okay. And this is the main branch. And the other branch which you have is feature in this case, right? Both are sharing the history up to B, right? From B, both of the main branch and the feature branch are sharing the history. The B, C, D will be included in E and F as well, and for A as well, right? Now let's see what will happen after you merge it. So you have completed your work, the development work inside this particular feature branch, and now you want to merge it to your main branch. So let's redraw it once again quickly. C, then D, then you have E, and then you have F. Now whenever you are trying to merge it, a new commit will be there, which is G, right? And Git will connect the branches, right? The feature branch and the main branch will be connected now. And a new commit G has two parents now. So this is the parent 1 and this is the parent 2. Correct? So you have understood one key point over here is, so let's say key points which I want to discuss over here is Git history is not a straight line, because every developer is branching off and then they are working on particular feature and then they are merging it. So the timeline is every time the timeline is not linear, right? It does not follow a singular chain. Second key point is branching is often cheap, correct, and fast. Third is Git is not copying files. In this case, when you are seeing that, in this case, if you see, whenever you are creating a new branch, then the history up to B, right? The DCB will be shared by the EF and the A as well. But in this case, what is happening is DCB is actually not getting copied to E and F. It is just a pointer. In this case, you see, it is just a pointer, right? It is just pointing to it. So the same B is pointing to A as well and with E as well, right? So it is not replicating the file again to the feature branch. Instead, it is pointing to it, creating a graph-like structure, right? So commit graph, you should take away a point over here is commit graph is not linear every time, right? And why this is powerful? Because branches are just new pointers. We have discussed, right? So let's say I want to discuss the pros, or let's say powerful conclusion, which is branches are just a new pointers, because it is not replicating the file, it is just pointing to A and E, right? Next thing is merging is just connecting to those pointers, connecting pointers, right? It doesn't mean that you are trying to merge the files, right? At a broad level or at a higher level, if you see over here, when I was merging it, so G became a new commit, right? So every time whenever you merge your changes to the main branch, there's a new commit, right? It is not like that you are creating the same commit, right, and using the or replicating the file and then you are merging the file. You are just maintaining the pointer to a new commit, which will then act as a merger to main branch and to the feature branch, right? No files are getting copied. This is for sure understood so far. Now the next is branch is lightweight. So now you understood why branch is lightweight, correct? So with this, you have understood that how Git tracks the history, right? And what is the commit graph concept. In the next video, we will connect this internal architecture with something you use every day, right? Which is the working directory and the staging directory, the staging area, and then your repository, right? So whatever internal architecture we have discussed so far, the commit graph concept, right, the SHA hashing, then we understood why Git is fast. Also the internal architecture, the most important ones, which is the commit object, the tree, and the blobs, right? We are going to connect this with the something you have, like you use it every time, right? The working directory, the staging area, and repository. You actually use it in daily life, and once you see how those interact with blobs, trees, and commits, right, Git will become very easy to learn. So if you like this content, subscribe to my channel, and we will see you in the next one.